This is a review of oxidation reduction chemistry and an introduction to our electrochemistry, chapter 20. Oxidation is the loss of electrons, and reduction is the gain of electrons. This is assuming that electrons are transferred from one thing to another in a chemical reaction. A couple of simple ways to remember this is oil rig, oxidation is loss, or reduction is gain. And Leo, the lion, goes grr. Loss of electrons is oxidation, gain of electrons is reduction. Deciding whether something loses or gains electrons is sometimes kind of difficult, and that's what we're going to take a look at as a review today. There are two more terms we need to talk about, and those are things called oxidizing agents or oxidants and reducing agents or reductants. Oxidizing agents are the things that cause something to be oxidized. And since oxidation and reduction always occur in pairs, the thing that is the oxidizing agent is actually being reduced. So the thing that's the oxidizing agent is the thing that's actually being reduced in the reaction. We also call it the oxidant. The opposite is true as well. The reducing agent is the thing being oxidized, or the thing that's actually losing electrons. We also call that the reductant. Oxidizing agent or oxidant, reducing agent or reductant, or simply saying that something is oxidized or reduced are all interchangeably used terms and used quite a bit in chapter 20 when we describe redox reactions that produced electricity. So how do we know if a reaction is redox or not? Well, the way to know is if the charges of the elements or ions that are reacting change from reactants to products. And to know whether these charges actually change or not, we need to be able to assign oxidation numbers or charge numbers to every element in a particular substance. And there are some specific rules for doing this that we learned back in chapter 4. And we'll review them just briefly, and we'll actually do this sample problem where it asks what are the oxidation states or oxidation numbers in each of these substances. This is page 139 in your textbook back in chapter 4 where they actually introduce assigning oxidation numbers. And there are 4 rules that we'll go through to help you assign oxidation numbers. The first one says that an atom in its elemental form has an oxidation number of 0. Thus, an atom of hydrogen in the H2 molecule has an oxidation number of 0. Phosphorus in the P4 molecule is 0. So if you ever see an element by itself, always think an oxidation number of 0. The oxidation number for a monatomic ion equals the charge on the ion. So if you see K plus in a solution, know that it is a +1 charge. S minus 2 means that it has an oxidation state of -2. Rule number 3 says that nonmetals usually have negative oxidation numbers, although they can sometimes be positive. The oxidation number of oxygen is usually -2 in both ionic and molecular compounds. The one major exception is in peroxide, O2 -2, where each atom of oxygen has an oxidation of -1. The oxidation number of hydrogen is +1 when it's bonded to a nonmetal and -1 when it's bonded to a metal. The oxidation number of fluorine is always -1. This is a nonmetal that you can be pretty certain about that it has a -1 oxidation state. There are a few other general rules of thumbs. Halogens, when with a metal, are generally a -1 charge. A good rule of thumb is that chlorine is -1 when it's with a metal, but when it's with nonmetals, it can sometimes be different things. And so those are just some general rules of thumb that you can follow with chlorine and with hydrogen and with fluorine being -1, general rules. Now, sometimes they change. Here's a good rule to help you determine what the oxidation numbers are. The oxidation numbers of all atoms in a neutral compound is equal to 0. The sum of the oxidation numbers in a polyatomic ion equal the charge of the ion. So if you look at this ion, H3O plus, the hydronium ion, you can see that it must add up to +1. 3 hydrogens and 1 oxygen must add up to +1, meaning that hydrogen must be +1. There's 3 of them. Oxygen is -2, like it almost always is, and that turns out to be a +1 charge. So you can use this summing of the oxidation numbers to help you determine what the charge is on other elements inside of a particular compound, ion, or polyatomic ion. Let's take a look at some samples now. What are the oxidation states of each atoms in these substances? And we'll take a look at a few of these right now. Let's look at cyanide, Cn-1 right here. Now, as a general rule of thumb, and this isn't always true, but as a general rule of thumb, nitrogen, which resides in group 15 on the periodic table, let's take a look at the periodic table really quick. This is group 15. Generally, they're a -3, but they can vary as well. And so let's just take a guess that it's -3. If we know that it has to add up to be a -1 charge, then carbon must be a +2 charge. And we'd probably be correct. That's a good guess for what we know right now. Let's take a look at HNO3 and what each thing would be in HNO3. Oxygen, we generally know, has a charge of -2. There are 3 of them in this compound, or in this molecular formula. Nitrogen, we might not know its charge for sure. Hydrogen generally has a charge of +1 with nonmetals, and there's 1 of them in the compound. Well, if we know that oxygen adds up to be -6, and we know that nitrogen is a charge that we don't know, and there's 1 hydrogen in there with a +1, we can look back at the formula. HNO3, nitric acid, has no charge, so we know it must add up to equal 0. That means nitrogen must, in this case, have a charge of +5, a stark difference from the nitrogen that we just saw in the cyanide polyatomic ion. And nitrogen can do that. So can other things. S8, well, this is in its elemental form. Things in their elemental form have an oxidation number of 0. SCl2, well, as a general rule of thumb, chloride ion has a charge of -1. And since it's more electronegative than sulfur, we'll give it the benefit of the doubt and give it the more negative charge. There are 2 chloride ions in here, or 2 chlorines. So sulfur plus -2 must add up and equal 0. If you look, this compound has no charge on it, or this formula right here. And so sulfur must be +2 in this case. Normally, you'd look at the periodic table and you'd say, oh, sulfur's right below oxygen. It's going to have a -2 charge. And you'd normally be correct. But when it's together with chlorine, which is more electronegative, sulfur takes on the positive charge. How about SO4 2-? Well, we know that it's got to add up to -2 because it's got an overall charge of -2. And the general rule of thumb says oxygen's -2 except for in peroxide, and there happen to be 4 of them in this polyatomic ion. So what must sulfur's charge be? Well, in this case, sulfur's going to have to be 6, right? 6 plus -8 adds up to -2. So here we've seen sulfur be +2, also +6, and other times we'll see sulfur be other charges as well. And that's what makes oxidation reduction actually happen, is that charges can change on various elements or atoms of elements. Well, what kind of reactions are redox? Well, you know quite a few reactions that are redox already. For instance, combustion reactions. CH4 plus O2 making carbon dioxide and water. These are all combustion reactions. All hydrocarbon combustion reactions are redox because oxygen here is in its elemental form. It has a charge of 0. What kind of charge does oxygen have over here? Well, it's got a -2 charge. Oh, it looks like oxygen's gone from 0 to -2. It must have gained some electrons, and so we say that oxygen has been reduced. Well, oxidation reduction, remember, always occurs in pairs. So if something's reduced, something must have also been oxidized. Well, if we assign oxidation numbers, we can find out that another element is also changed. And we'd find out that carbon has changed here. Hydrogen, since it's with a nonmetal, has stayed the same as a +1 charge. Let's talk a little bit more about other types of redox reactions besides combustion. Besides combustion reaction, there are also reactions that are redox reactions that you know that are called single replacement reactions. Single replacement reactions lots of times happen when you have a metal and you add it to an acid. A metal to an acid lots of times takes that solid metal and it will make it have a charge. For instance, if I take zinc and I put it in hydrochloric acid, now I'll make some zinc chloride and some H2 gas. Zinc had a 0 charge right here because it's in its elemental form. Over here, zinc has a +2 charge. Hydrogen here has a +1 charge, and over here, hydrogen is an element by itself, and it has a 0 charge. So from this side, we can see hydrogen has gone from +1 to 0. It's been reduced. Oxygen's gone from 0 to +2, and it's been oxidized. So single replacement reactions can lots of times be redox reactions. Now you saw a number of other redox reactions in our qualitative analysis scheme that we did just in the past week or so. But let's look more in depth at the life of an electron in a redox reaction and what actually happens to those electrons. Here's a single replacement reaction that we have occurring, not necessarily with an acid, but with magnesium metal and some copper sulfate. This is a single replacement reaction, and what we'd expect to happen is this magnesium would come over here and it would replace, as we said, we'd normally say, the copper in the solution. And we'd make some magnesium sulfate and we'd make some solid copper. Now, if you write this in a net ionic form, we'd break this soluble magnesium sulfate up, and we'd end up with Mg+2 and some Cu solid. Notice magnesium has gone from 0 to +2. Copper's gone from +2 to 0. Copper's been reduced. Magnesium has been oxidized. What about the reverse of this type of reaction, though? If we took copper and we put it into magnesium sulfate, well, now we'd expect copper to become copper +2 and magnesium to become magnesium charge of 0. And we'd expect magnesium to be reduced and copper to be oxidized. Well, which one actually happens? Which one actually has the electrons that are transferred from the magnesium here, losing electrons, to the copper, or from the copper here, losing electrons to the magnesium? Well, I have some samples here. This is copper sulfate solution. Let's zoom out just a little bit. Notice it's nice blue hue. Copper solutions generally are blue. And I have a piece of copper wire here as well. And here's some magnesium sulfate solution. Notice it's a clear colored solution, and I have a strip of magnesium here as well. If I take the magnesium and I put it into the magnesium sulfate, we'd assume nothing would happen, and that's exactly what happens, is absolutely nothing. If I take the copper and I put it into the copper sulfate, nothing happens there as well. Copper's not going to react with the copper ions that are in solution. Magnesium's not going to react with the magnesium ions in solution. But what happens if I take the magnesium and I put it in with the copper sulfate solution? Well, if you look at the reaction that we had right down here, we would expect that the magnesium would react with the copper. Magnesium would react with the copper sulfate, and we should get some magnesium ions. We should see the magnesium dissolve, and we should see solid copper forming. Now I'll take the magnesium and I'll put it in solution, and I'll kind of move it to the middle. Maybe you can see some bubbling taking place, and if I zoom in just a little bit more, maybe you can actually see some solid forming onto the magnesium strip. You can see it kind of falling off and it looks like there's something dirty that's happening in solution, that's actually the copper forming onto the piece of magnesium metal. And the magnesium is dissolving as well. Now what about this solution? What about the magnesium sulfate? If I take this piece of copper that I have right here and put it into the magnesium sulfate, we'd think that this reaction would take place right here. Copper plus the magnesium, it's going to make some copper ions and some solid magnesium. But when I put this into solution, something kind of amazing happens. Well, you might not think it's amazing. It's actually nothing happening, and you might say, well, that's a boring reaction. But it's kind of a striking thing for chemistry, because even though we can write this reaction, it doesn't happen. Why doesn't it happen? In this reaction right here, you can see there's all kinds of bubbling and fizzing going on. We've got a reaction occurring. We've got some copper forming. Maybe you can see the solid copper on the magnesium. It looks pretty dark on the film, I'm sure, but it actually has kind of a copper color to it. But here, we've got nothing occurring, no reaction happening. Why do some reactions that we can write occur and some reactions that we can write don't happen? Well, scientists wondered this as well. And so they took and they ranked these substances. They ranked these substances that transfer electrons. And they ranked them according to their ability to oxidize or reduce things. And generally today, the way things are written is in terms of their ability or their potential to be reduced. Their potential to be reduced. And if you look at this table, this is called the standard reduction potential tables for aqueous solutions at 25 degrees Celsius. It's called standard, of course, because we're at 25 degrees Celsius and we're looking at 1 molar solutions and we're at 1 atmosphere of pressure. And if you look at this, you can see there's actually a numerical rating system for substances to undergo reduction. In other words, the gain of electrons. Cobalt gaining some electrons to become cobalt plus 2. Gold gaining 3 electrons to become gold solid. Well, these standard reduction potentials actually are an arbitrary rating system based on hydrogen. Hydrogen right here is arbitrarily given a value of 0 potential to be reduced. Now, there are a lot of things that have negative potentials to be reduced. In other words, they're harder to reduce than these things. If we look at this chart, you can see magnesium is listed down here as having a reduction potential of negative 2.37. And if you look at copper, copper has a potential to be reduced of positive 0.34. Well, since this is a table of a ranking system, the one with the higher number up here is the one that has the best potential to be reduced. Copper, remember, in our solution was copper plus 2 ions. It wanted to gain 2 electrons. It wanted to be rigged or reduced. Reduction is the gain of electrons. Magnesium, on the other hand, was a solid. Magnesium wanted to go from magnesium solid to magnesium plus 2. And since it had a lower reduction potential, it actually was the thing that wasn't reduced, but it was the thing that was oxidized. Whenever you have two things reacting together, you can always look at this table. Whichever one has the higher value is going to be the one that's reduced. Whichever one has the lower value, that's the one that's going to be oxidized and is going to lose electrons. Well, in our next screencast, we'll take a look at, can the electrons that are transferred in a redox reaction be used for anything? And as a matter of fact, they can, and they can be harnessed. And the traveling of the electron can actually be used to do some energy or some work for something. You see right here, we've got some reactions that are going on, and we've got a light bulb up here, so you know it's going to cause something to happen.